Ladies and gentlemen, welcome back. This is Chapter 18 of Statistics Modeling Our World Curriculum, and we are talking about sampling distributions. So in the previous videos, you saw categorical variables or using proportions to make a sampling distribution. Okay, proportions being a categorical variable. So we created those sampling distributions for a categorical variable. So the question here is, what about quantitative data, right? The normal sampling distribution model is very useful. We want to be able to use it for quantitative data as well, and it turns out we can. Remarkably, the model that you use for the categorical data is very similar, extremely similar, to that you'll use for the quantitative data. Okay, it's almost the exact same model. So, like any statistic computed from a random sample, a sample mean also has a sampling distribution. The same idea of what we did with the proportions. We're going to sample multiple times, and we're going to calculate the mean every time and make a distribution from that. We can use the simulation to get a sense for what the sampling distribution might look like. So let's take a look at the simulator. And I believe I need to do this here. Okay, so I go through this one in my classes, but we'll do a couple things here. So up top, we have a parent population. This can be quantitative data, any set of quantitative data. So it's my parent population here is a normal model. Okay, it has a mean of 16, and it has a standard deviation of 5. So just like what we do with the proportions, we're going to take samples from this data. So what we're doing here is we're animating, we're seeing that we're taking 5 numbers from this population, and then we're dropping the mean down here. So we can do this multiple times, and every time we hit the button, we're drawing a random sample from the top and dropping the mean down in this new distribution. Now notice as we do this that most of the numbers are coming from the middle. Like this one's a little bit different, but most of what we're getting is from the middle, and that's because that's where most of the data is located. But we do get an extraneous one over here every once in a while. But notice that when we do that, it's still dropping the mean somewhere in the middle, because the number of data points in the middle is not being dragged significantly by this one over here. So as you sit here and do this over and over and over again, which we can continue doing it this way, we're seeing the means get dropped. But we can also skip ahead and do this a little bit faster. Going by 5s, we lose the animation, but you can see that the means start to form that same normal model. So now I'm doing 10,000 samples at a time here. Let's do 100,000 samples at a time here. Notice that we make a normal model. However, this normal model is not the same as the normal model up here. This one has a mean of 16 and a standard deviation of 5. This one has a mean of 16, so the centers stayed the same, but the standard deviation dropped to 2.24, right? The standard deviation, we lost some of that, the variation there, because of what I was saying earlier. When we have these data points that are sort of extraneous out here, they get balanced out by the values in the middle. So our standard deviation does drop down to 2.24. And this phenomenon happens no matter what the population looks like, right? We have a skewed distribution here, and again, we can draw samples from that, and we can sit here and look at the means. But if we do this many, many, many times, the distribution is relatively normal. There's a very small skew over here, but not enough that we wouldn't call this a normal model, okay? And again, the mean of the top equals the mean of the sampling distribution. The standard deviation of 6.22 dropped fairly significantly. So the centers remained about the same, but the standard deviations are dropping. Again, doesn't matter what distribution we do this with, right? There's a uniform distribution. That one comes out to be really normal. The means stay about the same. The standard deviations drop fairly significantly. It doesn't matter what it looks like. We can make kind of a crazy, like, three-modal thing that we've got here, and we still end up with something that is relatively normal in the long run. We can really mess it up if we want to, like, make something super bimodal, and that does cause some problems, but notice that it's still a vaguely normal-ish shape. So we can mess up the sampling distributions with really bimodal distributions, but for the most part, everything that we're going to do is going to end up being a normal model. And even this one that has these weird gaps, notice that the centers still ended up being the same, and the standard deviations still dropped fairly significantly. Okay, so these sampling distributions exist for quantitative data as well as the categorical data. However, they're not the same. They're not the exact same normal model. Okay. However, this phenomenon where it always ends up looking, the sampling distribution always looks like a normal model, leads us to a theorem, and it's one of the only theorems that we look at in AP statistics. But that theorem basically states that the sampling distribution for any mean becomes more nearly normal as the sample size grows. We call this the central limit theorem. Okay. As long as our observations are independent and collected with randomization, the data will be good. It doesn't matter what the shape of the population looks like, because the sampling distribution will always end up being a relatively normal model. Right? And we call this the central limit theorem, and it's a surprising and a little bit weird, especially those ones where the population gets really weird. But not only does the histogram of the sample mean get closer and closer to the normal model as the sample size grows, but it's true regardless of the population distribution. It does work better and faster when the population model is close to the normal model, but it does work for any population size. Okay, so there's our sort of official. This is what the central limit theorem is. The mean of a random sample is a random variable whose sampling distribution can be approximated by a normal model. The larger the sample, the better the approximation will be. So there are some assumptions and conditions that we need to have to do this with quantitative data. Like there was with categorical data, we do have them for quantitative data as well. They are very similar assumptions and conditions. We need our data to be collected randomly. So if we're doing the experiment ourselves, we need to make sure that we're using good sampling practices, collecting random data. If you're doing problems in AP land, you need to make sure and check that somewhere in the problem it states that this is random. Okay. We also have a sample size condition, and we need to say that it's large enough. We're gonna say for right now, we just need to say that it's large enough. We will go into more detail on this when we look into quantitative, the quantitative data. What's the word I'm looking for? Techniques that we're gonna look at in chapters 21 through 24. Okay. For right now, we just need to be able to make sure that the sample size is large enough. We should, to give you kind of an idea, right? 40-ish is generally pretty good in terms of a sample size. However, if sample sizes are small, as long as the population is believed to be fairly normal, we can still check off this condition. Okay, so our assumptions and conditions to use this model: we need randomization and we need the sample size to be large enough. Oh, that came in weird. So Like I said earlier, they're both normal models, the categorical data and the quantitative data, but which normal are we talking about? So it says the distribution of any mean is approximate, or proportion is approximately normal, but they have different models. For proportions, we said that the sampling distribution is centered at the population proportion, right? We called that p hat. Okay, our distribution had a center of p hat. For means, this is going to be centered at whatever the population mean is. So the my mu, and so that's the same. However, what's different is our standard deviations. The proportions, our standard deviations, we follow the formula, the square root of PQ over N. We obviously can't have that same standard deviation for quantitative data, though, because we don't look at proportions with quantitative data. So as it turns out, the standard deviation for a sampling distribution for quantitative data is the standard deviation of the population divided by the square root of the sample size. So that simulation that we were doing earlier, you can actually calculate what the standard deviation of that sampling distribution will be by doing this calculation here, the standard deviation divided by the square root of the sample size. And that's where we're going to stop this video. We're going to have one more video in this series where we do examples of quantitative problems. And so that'll be what's coming up next here. Thank you very much for watching. If you have questions, comments, concerns, please make sure you address them. And I will do my best to help you out. Otherwise, again, have a great day.